Thanks so much. So today I want to talk about three things maybe. First is to make a few observations about big data in general. Second is to talk about this Myria system. And the third one, which I'm not sure I probably won't have time for, but given the audience and given also the session we're in, I want to talk a little bit about some of the work we're doing in graph clustering. And if I only get a chance to advertise it, we can talk offline about it. I'm always excited to chat about our work in that space. So I work a lot with scientists in astronomy and oceanography and so on. That's where we derive a lot of requirements and we derive a lot of our research agenda from them. And one project that I wanted to bring people's attention, if they haven't heard of it already, is the Sloan Digital Sky Survey, which is now over, but has ran for sort of 10 years and sort of collected a whole bunch of data. And the key idea that made it one of the most productive astronomy facilities sort of in history was the fact that they put all this stuff into a database and served that back out to the world. It wasn't so much just about the telescope, it was about the way they sort of handled the data. But, you know, this required some sort of a complicated schema, and it involved a Turing Award-winning computer scientist partnering with a leading-edge astronomer who was an expert in computing, Alex Zillay, and it required sort of a complicated cyber infrastructure they had to build out. And one of the things that drives my research agenda is, you know, how can we deliver the next 1,000 little Sloan Digital Sky Surveys for anyone who might need one, right? So as opposed to having to require these big brains to sort of partner up and spend a bunch of years working on this, how can we do this kind of at scale in the sort of long tail of science? All right, so keep that in mind. We ask this question a lot for these scientists that we work with. You know, we say, sort of, how much time do you spend, quote, handling data as opposed to, quote, doing science? And we don't try to make this precise, but you can kind of see what we're going after here. So what do you think the most common answer is?
80%.
Anybody else? So you guys are right on, right? So they don't even blink. They're like, oh yeah, I spend 90% of my time, you know, doing something that I don't consider science. And this, to me, as a computer scientist, is pretty embarrassing, right? This means that our tools, despite what we're doing, sorry? How do we get the number 90%? We ask them the question and they say 90%. We didn't calculate this. That's why it's in quotes. It's their rough estimate of what they do, right? It's not a quantitative result. It's an anecdotal result, but it's I find it still fairly compelling. In fact, the one meeting I was in where the numbers came out differently, I was asking this question because I do this a lot, and they were saying things like 30% and 20, 40% and so forth. So what do you think was true about all the people in that meeting? Yeah, so it was in the medical domain, and they were all like, sometimes you know how medical funding works, but there's kind of the kingpin PI and then a whole team of people below them, and these were the PIs, right? And so even the PIs who essentially had, you know, the postdocs did literally all the work, they still sort of reported that they spend about 30% of their time doing things they don't consider science, right? So this is troubling to me, I think, and sort of motivates some of the work we do. And another way to put this from a slide put together by Dan Halpern, who works with us on this team, who's got some great perspective on this. This is, you know, every computer science paper you've read on systems, right, is old system is slow and your system is faster but not as fast as our system down here, right, on some number of benchmarks. But the reality is this, right? Here's the same 3 bars, right? And here's what people are actually doing in practice. Something that's like many orders of magnitude slower than your sort of state-of-the-art, super fast Formula One race car that you're designing, right? And so I'm interested in sort of tackling this problem as well, right? Not just sort of settling for in the best context in the world, you know, how fast can we go? Rather, in the realistic context, how fast can we go? Okay. And just to say that this isn't just sort of completely abstract. We get reports from people that we work with that are like this. I don't necessarily expect you to read all this text, but the idea is that this is someone reporting to us when we said, hey, you might want to try out our system. We think we can maybe help you. Tell me how you sort of spend your time and what kind of problems you're having. And they were sort of arguing that, like, look, I don't think your system can help me because what I do is really hard stuff. For example, building indexes on things and focusing on data retrieval and cutting the data into chunks and having to order the steps of the processing just right. And our reaction, of course, was this is exactly what we do automatically in all the systems we build. And so their estimate here was that they were spending, you know, about 30% figuring out how to do things and 20% getting files and getting the right time, blah, blah, blah. By their own estimate, when they were trying to sort of make the opposite point than they ended up making to me, they guessed about 3 months on issues of scale and file handling and feature engineering and so forth. This was not the science. This was not the statistical modeling that they were really paid to do. And this is all stuff that we already know how to do. And so sort of back of the envelope calculation, you know, maybe $75 million annually from NSF going to fund postdocs to spend their time doing things that they aren't trained to do. Okay, so this is a problem. I think we need to solve it. Admittedly, I'm belaboring this, but let me bring one more point up. In this whole data science, big data world, more from the commercial side, you'll hear people talk about a three-step kind of pipeline. There's, preparing to run the, I'm not going to use this, preparing to run the model, actually running the model, and then sort of interpreting the results. And so where do you think all the time goes? One, really, right? This is not surprising. Anybody that actually does this work for a living will not even, anybody that says 2 is the thing that keeps them up at night is lying or naive, I think. And so this is what we sort of hear, is that this is 80% of the work, and then the joke is that this is the other 80% of the work. All right, so getting the exact right model is not the problem. And so what I claim here is that, intentionally trying to be a bit provocative perhaps, is your cool algorithmic problem is never the bottleneck in practice. Maybe not never. Very rarely the bottleneck in practice. That's my first observation about sort of what's going on in big data. A second observation has to do with this. So something that all databases can do is this kind of thing called algebraic optimization. How many people know what I mean when I say algebraic optimization? How many people can guess what I might mean by algebraic optimization? A few more, okay. So just with integers, if you have this expression at the top, right, you could just brute force evaluate this thing, and then you plug in a value for z. Sorry, I guess I have an old version of the slide. Say I give you a value of z, and you need to now evaluate this. You could just plug in z and brute force your way to compute in. Or you might sort of get cute and notice that there's some algebraic laws that apply, and then when you add 0 to something, you don't actually have to compute the addition. You can just drop that off. And there's an identity for x divided by 1, and there's a distributive law that might simplify things, and so on. But in practice, you would never actually do this with integers, right? You don't do this kind of symbolic, the CPU is not going to do this kind of a symbolic reasoning because it's way more expensive to do the symbolic reasoning than it is to just evaluate the thing. However, if instead of integers, these were, terabyte-sized tables, it's no longer a luxury. It's absolutely a requirement to do this kind of symbolic reasoning. And and so you simplify this down, and now you have sort of 2 operations instead of 5, and maybe you avoid this expensive division operator or whatever. And every database in the world does this automatically when you issue a query, right? It's considering various plans and choosing the one that it thinks is best. And I think we give up on this too early when we move into the sort of big data regime and go back to kind of a low-level way of programming where we put all the onus on the programmer to figure everything out. And that's fine. We saw earlier today in the tutorial that there's kind of a dichotomy, and this is leading to my observation that I don't think the dichotomy is true, where there's kind of, well, there's SQL queries and then there's, ML, and those are different systems, different requirements, whole different balls of wax, and I don't really buy it. I think that the line is blurry at least, and maybe even could be erased completely. So we see people who don't write a line of code in any language whatsoever, in any programming language, writing these big, hairy 40-line SQL queries that do sort of like interval arithmetic on biological sequences and computing things. So there's complex stuff you can do in SQL. And we have some examples where we show people taking their R code and translating that into SQL and showing how it kind of scales better and it's faster. And I don't know if people are familiar with this Galaxy engine. Have you heard of this? Had a pin? So it's a big workflow engine for mainly for bioinformatics, but more general things too. And recently we sort of noticed that they were some of the black box operators that they provide are things like select and project and join, which if you're familiar, those are operators in the relational algebra. So they sort of started off with high-end bioinformatics algorithms and reduced down to very simple operations that databases already support. And maybe surprisingly, maybe not, we can take these sort of big complicated things and rewrite them as queries, and the world is sort of a better place for it. And if you add a little bit of iteration, which is where we're trying to go with this Myria project that I'll get to in a moment, if you put loops in here too, now you can express things like k-means and ML and so forth. And every line of code in this business, I don't expect you to read this, but trust me that it's all relational algebra. Every line of code here, we know how to scale more or less infinitely, all right? Okay, so my observation too is that this whole SQL versus ML is a false dichotomy. I think there's room for a system that can sort of do both. And really, I don't mean SQL. I don't really care about the language SQL. What I care about is this underlying formalism of relational algebra. And really, ML is probably linear algebra, maybe, if you'll forgive me. All right, so third observation is I did some a quick kind of meta-analysis of big data systems literature, sort of mainly focused on my field, because that's what I know, and tried to write it all down, and this was too hard to look at, so I tried to draw a picture of it. And it looks maybe something like this, right? So in 2000, time is going down here, and the blue lines are sort of, they report being 100 times faster on some set of problems. The orange lines are they're faster, but maybe it's a factor of 2 or something. And the dotted lines are maybe inconclusive or sort of comparable or something. And the point I guess I want to make is that for a few years there, everybody was sort of 100 times faster than Hadoop, and you could publish a paper by choosing your favorite design flaw in Hadoop and fixing it, and then showing you were 100 times faster. But there's diminishing returns now, that we've sort of exhausted all those opportunities, and there's a lot more of these dotted lines and orange lines down here in modern times, and we don't quite know what's going on as much. So when you see people reporting their results beating up on Hadoop, it's not very interesting anymore, and you shouldn't let people do that. Moreover, we need more professional industrial strength experiments to compare these guys, and we don't have that. Okay, so third observation is anything based on Hadoop is 100 times slower than the state of the art, and it might still be okay to use in practice, but don't assume that you're doing as fast as we know how to do. And further, the corollary is that the rest of it is not so clear. It's not obvious what's better than what when you're not talking about Hadoop. Okay, so what I think we need here, and part of what we're trying to do with Myria is to have a big data sort of middleware, where we address this problem that these big data experiments are ridiculously labor intensive, right? You have to sort of stand up in systems with real world realistic applications and sort of compare them all and build a big matrix of results. And nobody does this, so instead they just sort of beat up on Hadoop. We probably acknowledge that there's not going to be a one size fits all solution in the back end. You might have different systems out there that are good at different things, and we need some way to reason about both of them together to solve single problems. And then I think there's a resurgence of kind of the notion of a federated, maybe not database, a federated systems. When I'm talking about a database crowd, I can say database, and they know a general version of it. When I'm talking about this crowd, I don't necessarily mean like MySQL. I mean sort of the broader view of this. But a federated sort of view where you might have some data over in one university, and we have some data in another university, and we need to sort of do query processing across them. And so this middleware notion is something that we didn't think existed, so we're trying to have that as a component of this Myria project. Okay, so we have a whole bunch of people involved with this, a lot of students. Dan Halpern here, I want to point out, is sort of the technical lead of the project and has been pushing it along. And so what it is three pieces. There's this MyriaQ, which is the part that I've been most interested in, which is kind of an optimizing compiler and kind of a middleware for taking in multiple iterative source languages and compiling them down to target multiple different backends. Things like our own backend, Spark, a system called Grappa at UW, Serial C++, in some cases that's useful, and so on. And then MyriaX, which is a state-of-the-art, parallel shared nothing, iterative kind of relational execution engine, where we are able to inject the algorithms that we develop in sort of alternative work and get them right into the system in order to take advantage of them. And then kind of a web front end where we have an interactive IDE as well as a RESTful interface, so you can sort of fire queries from your Python client or your R clients or so on. And we want to stand this whole thing up as a service in order to get scientists to actually use it, right? Because if you say, I've got this system that beats Hadoop, and you can go to here on GitHub and download it yourself and install it on your own cluster, the people the oceanographers we work with aren't going to do that. But if you say, here's a URL, if you click on that URL, you can actually run some queries right now, they will. And so we're really kind of committed to delivering this as a service. All right, so the architecture looks something like this. I'm not going to spend too much time on this, but different languages come in at the top. We sort of parse them and optimize them and can generate different backends. Our own backend, this MyriaX thing, is all in Java. On every individual worker, there's a relational database, but it's not important as a relational database. It's really just to support indexing. We don't really use the relational database for its own features. And then the parallel processing is all handled by us at this layer. All right. And we also support pulling data from HDFS, which allows transitively to pull from like S3 on Amazon and all sorts of other places as well, which is nice. It's kind of becoming, for better or for worse, it's becoming kind of a de facto standard for sharing large data sets. Okay, and so this red line is what is going to be on the next slide, is where I'm sort of focused with this middleware story. This is still just sort of a cartoon zooming in, but we support our own backend, of course. Again, I mentioned this Grappa system at UW, which is a parallel kind of emulates kind of a shared memory environment on a big cluster, and you can do sort of low-level C++ programming, but they wanted a higher-level interface, and so we said we can provide that to you if you help us implement your version of the compiler, which we have a student working on that. We can generate serial C++, which, never underestimate how fast you can go with just tight loops directly in C. So in some cases, we wanted to not leave too much on the table by focusing on distributed computation only. So we have a paper in VLDB, I guess a year ago now, that showed that we looked at the workloads of how people are using Hadoop in the university settings, and some 80% of the jobs were under some size. What do you think size that was? How big are typical Hadoop jobs? I've been talking much. I need to ask more questions to keep you engaged. Well, just I guess the point I'm making is Hadoop's designed obviously for massive, massive data, and I'm leading the witness a little bit here, but the typical size is not that. Yeah, exactly. It's like 5 gigabytes, 10 gigabytes, and of course this now fits in memory nowadays, right? So people are overusing Hadoop, which is kind of hard to fault them. It's cluster and it's available, and hey, it works on big data. Why not use it for small data too? Because I don't want to learn two things. But if we compile down to something tighter and smaller that actually takes advantage of a single site resources, that would be better. So we wanted to make sure we had that capability in here as well. Okay, and then we can program databases, and we're looking now at SciDB, which is this array-based database thing. Fine. So let me give you a quick example of the kind of thing we're doing with this. There's a device called a C-flow. People heard of a flow cytometry? You know what this is? A little bit, not too many. So flow cytometry was originally developed for medical applications, and they take like blood or serum from a patient, put it in the back of a machine, pushes particulate matter single file through a really thin capillary. You shine lasers at the capillary, and by the absorption and refraction patterns, you can tell what kind of pathogen it is and therefore diagnose the disease. But this is sitting on a lab bench, and you have kind of unlimited time to process it, and you can do the engineering to push it through single file, and you're only looking for one of 3 different pathogens or something like that. These guys are using it for environmental monitoring. They built a new device from the ground up, turn it upside down, put it on the bottom of an ocean-going vessel, and in real time are monitoring the microbial populations of the open ocean, which essentially was completely unknown before they did this. And the reason, it's sort of surprising to me to hear that it was completely unknown. I was like, boy, you think they'd know that. But the reason is that the only methods they have to study this are satellite images, which are ridiculously indirect, right? They look at things like the sea color looks pretty green, therefore there's probably a lot of photosynthesis happening, therefore there's probably a lot of phytoplankton, or very sparse sampling where you take a little test tube full of water, freeze it, bring it back to the lab and look at it. And this gives you a kind of just painting out a continuous sort of stream. So fine, so the data gets pretty big. They can't do it single file because the boat's doing this, so the engineering is kind of too hard to get things that precise. So the data's a lot noisier. And so what you save in engineering, you have to make up in heavyweight analytics, which is where we sort of come in. And they make these kind of plots, and they want to cluster things in order to understand the basic structure of the microbial populations and understand how that changes with the environment. And there's a picture of the device and so forth. So punchline here is, we threw all this stuff into Myria. Previously, before that, they had been looking at a kind of individual cruises at a time and individual days at a time because it was just whatever they could sort of fit in memory or sort of handle comfortably. And we said, no, just load everything you have and ask any query you want, and we'll take care of it. And so, the quote here is, the 5-line MyriaL program was 100 times faster than some R cluster setup they had done. And yes, it's still anecdotal, but this is the kind of thing we're looking for. And in this particular case, it wasn't particularly hairy. It was basically expressible as a couple of SQL queries. Okay, so I want to pop over and see if I can give a quick demo of this thing to make it real. And I had demo by PowerPoint queued up in case something goes wrong, but it's live and you can go check it out. This is that particular query that I just mentioned on the C-flow, and I can, you have an editor here. You can look back at previous queries that have run. You can sort of review all the data sets. One sort of aspect here is every time you run a query, it creates a new data set. So we're just sort of constantly extending the schema with all results are saved. You never want to download a large result. It just gets stored in the system for further querying. Fine. The language here I didn't really talk much about, but it's kind of a mix of imperative and declarative, right? So you have one line of code here is a variable gets the result of an expression, and the expression in this case is a SQL query, but you can also do little list comprehensions like you can in Python and so on. But every one of these is a big parallel job that runs. So if you're familiar with like Pig and Hive and so forth, it's got a bit of that flavor, but it's sort of a custom language, and we have some tricks that we do. So I'm not going to care about the result here, but I can run this thing just to prove that it actually is sort of doing something. And it's running, it'll sort of count us some time, and in, I don't know, I think a couple of minutes it would finish. But the point I want to make maybe in the demo less than an editor, and just the fact that that actually is up and live, is that we want to lift actually algorithm design up as a first-class citizen. It's not, like the value proposition of databases is usually that you sort of fire a declarative query and it does all the magic and just gives you the answer and it does all the work. And I don't think that really works anymore in the sort of big data era for a couple of reasons. One is the users are a lot more sophisticated, right? These are analysts and data scientists and sort of fairly savvy people, and they want to understand more. Second of all, the data sizes are so large that when something goes wrong and the optimizer doesn't find the right plan or something's really, really slow, you've got to do something. You've got to be able to take some action. And databases don't let you do that. So we're trying to sort of think about how we can have an interface that allows you to do the kind of analytics you want. And so I won't spend too much time on this, but what this is looking at the actual query plan that gets generated from that program. That multi-line program all gets compiled into one big plan. This is the big parallel plan, and these plots down here show the number of workers active at against time, right? So here there's sort of 60 workers active, and then it kind of drops for a while and so on. And so you can automatically already get kind of a sense of how much work is going on. You want to see sort of all workers busy on all queries. Let me see what I got here. Yeah, so and this one here, so I can zoom in on just this one fragment, and I can take a look at some of this stuff, and I can see where the time is going. The 55% of the time is going to the shuffle producer. The number of workers is sort of steadily going down, and this is what individually each worker was sort of doing. And so you can kind of really get into a pretty low level of detail and see what exactly is happening. And one of the things I want to point out here, though, is that this arrow here between these fragments is sort of the intercluster, bisectional communication that's happening during the processing. And so how to look at this is that this is the source worker, and there's 64 of them in this case, and the target worker. Right, and this is each box is the number of tuples sent from worker I to worker J, right? And so the point here is that if you sort these guys like this, it's not too bad. They're sort of more or less balanced, and the whole sort of box is purple here. On the other leg, it's a little worse. You see this skew happening here. I did mention the data set here. The data set here is a social network graph. It's kind of a Twitter thing. So what this query, I just skipped over this, sorry. What the query is here is a triangle query, actually. So finding triangles in the graph, right? And so this first step, this first join here is finding every path of length 2 in the graph, right? So find all the edges and join them up and find the things common and count those up. So there's a lot of these in a graph. And you see that there's already some skew happening here where you have people that are very popular that have lots and lots of followers will tend to be a spike. But the real problem happens on the next step, where you get the fan in multiplied by the fan out. And so if you have a heavy hitter node that has a very high degree distribution, one worker in the parallel cluster is doing all of that work. And you can see that very clearly, right? This worker 9 had to handle, Justin Bieber is what we were joking is the analog of what's going on here. Ended up having to spray out tuples to all the other workers, and clearly is the bottleneck in this case. But the overall point I want to make is that thinking about these visualizations and thinking about how to bring this kind of performance analysis out to the user, to the end users, is something we're sort of committed to here, rather than making it a black box. Okay, and then I think that's maybe the only point I want to make about that. So I showed this earlier. This is sort of k-means language. There's one more example I want to kind of go through. This is a real example from some colleagues in astronomy that we work with. They do this process called sigma clipping, and it's not the most sophisticated thing in the world, but it does require an iterative process. And I just want to go through at least one example in detail about what I mean by iterative relational, using relational algebra techniques, but in an iterative context. So people have heard of this term, sigma clipping. I think it might be kind of specific to astronomy. I think it's pretty intuitive, but I'm not sure anybody else uses that term. So the idea here is that out of all these data points, take one standard deviation away and then filter out everything that's outside of those standard deviations, and then repeat, right? Find the mean again, take another standard deviation and filter, and keep going until it converges. Is that sort of clear? And they do this for astronomical images, right? So they're trying to get rid of the noise. They're trying to pound down the noise and focus on the point sources that they can actually identify, the stars and galaxies and so on. And so this is a standard sort of operation. So the point here is, why is this red? So this is a program written in MyriaL, in this language we have, that will implement this. And the reason I've colored them red is to say that although these are parallel steps, because everything's parallel, every line of code is parallel, they're all touching fairly large data sets, and they're all potentially kind of slow. If you're a database zealot, you might argue, well, hey, it's the optimizer's job to just figure it out and kind of find a better plan. But my point I want to make is that's not really possible in general, and you have to empower the programmer to come up with their own things. So here's a faster plan that does the same thing that in a cartoon, don't necessarily look at the code, but in a cartoon way, whoops, well, let me not stride through it since I'm a little low on time. The point is with some essentially human intuition, we can be smarter about how we process this on every loop and make sure that we never touch really, really large data sets in the loop. As now all the green lines are now touching small things, this is essentially an incremental kind of approach where you're only processing the deltas every time as opposed to the whole thing again on every iteration. Fine, and then maybe this blue line is something that could be fast if we have the right indexes and so on. But we still have the problem in that last line is still red. And here's an even more complicated, kind of fancier version that you could potentially write that we've sort of tested and ends up being fast. But the point I want to make is all three of these are valid implementations. All three of them are pure relational algebra. And it's not likely that this, quote, best one is something that you're going to automatically derive. And so we really want to empower people who are, even though you're in relational algebra land, you're still sort of designing algorithms, still thinking hard about your problem, and we want to give you the tools to be able to do that. Okay. So takeaways from this part, and then maybe I'll spend 2 minutes on, well, I guess maybe I'll spend 2 minutes on this graph clustering. Points we have a little bit of time, since I guess we have a little extra, since it's 30 minutes. Is that 3 minutes for 30? Well, we'll see. So the takeaways here is we have this thing called Myria's Analytics as a Service. We're really emphasizing lowering the barrier to entry. We want to empower this new breed of data scientists, analysts. We happen to be working with actual scientists in oceanography, but I think the same kind of role is starting to exist in commercial world as well, where you have people who are smart and invested in the data, but are not IT staff, right? They actually want the answers to their questions. And then with the key selling points here are the iterative processing, and we try to make sure that the internals are all very much state of the art. We have top algorithms and different kind of system design features that have come out of the forward edge of the literature. And then overall, we're trying to really blur the distinction between what's a query and what's an algorithm, and support algorithm design as a query. And I think relational algebra is at least as important as linear algebra in teaching this stuff. And the reason is, although linear algebra, you can sort of express everything and there's all these beautiful properties you can sort of prove about them, it's not always obvious that just because you can write it down in linear algebra, we know how to evaluate it quickly. In relational algebra, we have a bit of a head start there. A lot of these, when you express it as a relational algebra query, we've thought about how to optimize that computationally as opposed to just mathematically. All right. So maybe I'll stop there rather than diving into the graph clustering, and you can ask me about that offline. Thanks.